want to look now at the subject matter of Taylor polynomials and the resulting power series that come from Taylor polynomials and power series themselves. If you get a function f of x, which is differentiable at a, then f of x is approximately equal to the value on the tangent line. So if here's a, and here's f of x, right, we can approximate the value of f nearby as the value on the tangent line. And the value on the tangent line is given by f at a plus the derivative at a, x minus a. Right? Now, it might be more preferable to approximate this by, let's say, the best, so to speak, parabola through here. And in one sense, the best parabola for approximating f of x is f of a plus f prime of a times x minus a plus the second derivative at a times x minus a squared over 2. Right? Best in the following sense. This function right here, say p2 of x, has the same value as f does at a, the same derivative at a, and the same second derivative at a. You see that? Let's just compute here. P2 of a, when you put a in here, you get 0 here and you get 0 here, and P2 of a is f of a. Right? The derivative, differentiating this, let's compute P2 prime of x. This is going to be equal to the derivative of this constant. These are all constants, of course. The derivative of the constant is 0. We get f prime at a, the derivative of x minus a is 1, plus the second derivative at a, we get 2x minus a to the first, and the 2 cancels with the 2 here, so this is the derivative of p2 at x, and when x is equal to a, we get p2 prime at a, and it's f prime at a. Put a in here, this is 0. The second derivative of p at x, this is a constant, so its derivative is 0. We get f double prime of a as a constant, and then we have the derivative of x minus a. So the second derivative at x, at every point x for that matter, is the second derivative of f at a. So this is a polynomial of degree 2. It's got the same function value, same derivative, same second derivative as f does at a. Right? This can be generalized here to what's called Taylor polynomial. Pn of x equals to f at a plus f prime of a times x minus a plus the second derivative at a, x minus a squared over 2 factorial, plus the third derivative at a, x minus a cubed over 3 factorial, plus and so forth here, the nth derivative at a, x minus a to the nth power over n factorial. This is the nth Taylor polynomial, and it presupposes that the function f of x is n times differentiable. All right. Now a couple questions emerge here, and one is this. If we continue this indefinitely, we get what's called a Taylor series. And the question is, does the Taylor series converge? Does the Taylor series converge? And if so, does it converge to f of x at x? Let's just say we put a particular value of x in here, carry this out indefinitely, and take the limits. Does it converge to the value of p of f at x? All right. In a good number of cases, this is going to be true, and the usefulness of this is due to the fact that a Taylor polynomial only involves addition, subtraction, multiplication, and division. If you want to evaluate this at a particular value x, you subtract, you multiply, you divide, all right? And so you're always performing operations that a computer can do, which of course is what you want the computer to do, namely approximate a given function f of x by means of addition, subtraction, multiplication, and division. All right, so the Taylor polynomial gives rise to what's called a Taylor series. And the Taylor series can be written in summation notation like this. If we agree to write the zeroth derivative of f as f itself, then we have the first derivative and the second derivative and the third derivative and so forth. We also agree that 0 factorial is equal to 1. And we can write this as the nth derivative of f at a x minus a to the nth power over n factorial, and the sum starting at 0. If we just wanted the Taylor polynomial, we'd go up to capital N here. Otherwise, we'd go up to infinity if we want the Taylor series. Now, let's check that this is correct here. The nth derivative, the 0th derivative is f at a, and we've got x minus a to the 0 power. That's just going to be 1, and 0 factorial is 1, so that's the first term. When n is 1, we get the first derivative, x minus a to the 1 over 1 factorial. That's the second term. Second derivative, x minus a squared over 2 factorial. Third term, and so forth here. So this is the Taylor series of the function f expanded about the point a. Now, frequently it's convenient to use 0 for a, in which case the series is called the Maclaurin series. And it has a slightly simpler summation here. Sum n equals 0 to infinity. The nth derivative is 0, x to the n over n factorial. This is then the Maclaurin series. A is equal to 0, so we have x to the n, 0, and n factorial. We'll be looking at these as some examples, and the whole theory as to how the basic functions behave regarding Taylor polynomials and the resulting series. Now I want to look at three relatively simple Taylor polynomials right now, namely those for e to the x, sine x, and cosine x. And we're going to expand these about 0 so that these are really Maclaurin series here that we're going to be looking at. And recall then that what? F of x is approximately equals to the function at 0 plus the derivative at 0 times x plus the second derivative at 0 times x squared over 2 factorial plus the third derivative at 0 x cubed over 3 factorial and so forth here. The nth derivative at 0 x to the n over n factorial. All right. The function we want to look at is e to the x. And we want to do this at x equals 0. So it's a good idea to make sort of a chart here for e to the x. This is not going to be a big thing here. What you want to do for your chart is you want to put down f, the derivative, and so forth. But all of these are going to be e to the x. And then you put down the value at 0, e to the 0, which is 1. Huh? So if we made this chart out, it would be e to the x, e to the x, e to the x, e to the x, and 1, 1, 1, 1, 1. So now we want e to the x is approximately equal to the value of the function at 0 is 1, plus the derivative at 0 times x, that's 1 times x, plus the second derivative at 0 times x squared over 2 factorial, plus the third derivative at 0, that's 1 again, x cubed over 3 factorial, plus x to the 4th over 4 factorial, and so forth here, plus x to the n over n factorial. So there's the Taylor polynomial for the function e to the x. If you continue this on indefinitely, it turns out that this infinite series here at each x is defined as a series, and this converges at each x to e to the x. But faster, of course, near 0. So that for some values of x, this is not really it's not really convenient to use this to compute e to the x, and maybe resort to some other means. But near 0, this converges very rapidly to e to the x. All right, let's look at another function here. In this case, let's look at sine x at x equals 0. Right. And now what we want is f. This is sine x. And at 0, it's 0. The derivative is cosine x. The second derivative is minus the sine of x. At 0, that's 0. The third derivative is minus the cosine of x. And at 0, that's what? Minus 1. And now this repeats. So the fourth derivative is this at 0. Fifth derivative, sixth derivative, seventh derivative, eighth derivative, ninth derivative, 10th derivative, and so forth here. So we get that sine x is approximately equal to what? At 0, we have 0 plus 1 times x plus 0 times x squared over 2 factorial minus 1 times x cubed over 3 factorial plus 0x to the 4th over 4 factorial plus 1 x to the 5th over 5 factorial plus 0x to the 6th minus 1 x to the 7th over 7 factorial, and then this continues like this, plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial, and so forth. Right? Well, this converges right here. This converges right here to e to the x. This converges to sine x at each x. Again, faster near 0, because that's where the expansion takes place. Okay, cosine x. A function is cosine x. The derivative is minus the sine. The second derivative is minus the cosine. The third derivative is the sine. And then this repeats. So the value of the function at x equals 0 is going to be 1. The value of the derivative is 0. The value of the second derivative is minus 1. Third derivative is 0, and so forth, and this repeats. So cosine x is approximately equals to 1 f of 0. The first derivative is 0 times x, which is 0x, minus 1 times x squared over 2 factorial, 0x cubed over 3 factorial, 1x to the 4th over 4 factorial, 0x to the 5th, minus 1x to the 6th over 6 factorial. And then this goes plus x to the 8th over 8 factorial, minus x to the 10th over 10 factorial, and so forth here. And again, this converges, and it converges to cosine x at each x. Okay, something that you can try, we're not going to really do here, and that is that if you start with a function that is a polynomial, and you take its Taylor expansion, if there's a polynomial of degree and you take the Taylor expansion to degree n, you can end up with the function right back again. That's to say that two polynomials of degree n have the same value at a point, derivative, second derivative, and so forth up to the nth derivative, then they have to agree. Okay. We want to look now at Taylor's theorem. Taylor's theorem tells you, gives you a way of determining how well a particular polynomial approaches the function x, or approximates the function x. So, the theorem is as follows. suppose the f of x is n plus 1 times differentiable on closed interval AB. Now we're going to work to the right of A, but you could also work just as easily to the left, for example, of B here. Pn of x is equals to the summation k equals 0 to n. This is the Taylor polynomial. F, the kth derivative at a, x minus a to the k power over k factorial. Then the question is, if this is the Taylor polynomial about a, then how good is the approximation at b? Like I say, we're going to the right here, but you can just easily go to the left. The conclusion here then is this. Then f at b is equal to Pn at b plus an error term here. The error term is given by the n plus first derivative of f at some point z in the interval AB times b minus a to the n plus 1 over n plus 1 factorial. So this is for some z in the interval AB. So what this asserts is that there is a z in the interval AB, so the value of f at b is this. Now this says, for example, if the n plus first derivative is not too large, b minus a to the n is not too large, or b minus a is not too large, take it to the n plus 1 power, it's not going to be large. N plus 1 factorial is going to be a large number. This approximation is going to be very good if the n plus first derivative doesn't get to be too large. This is the remainder here, sometimes written as Rn plus 1 right, at B. Okay, the proof. What we do is the following. We define M as follows. F of B is equal to Pn of B plus M times b minus a to the n plus 1. Right? This, whatever f of b is, that's to say m, whatever f of b is, m is going to be equal to f of b minus Pn of b, whatever it happens to be, divided by b minus a to the n plus 1. So this defines m. Now we let g of x be defined by f of x minus Pn of x minus m x minus a to the n plus 1. We want to show that there is a z so that m is equal to the n plus first derivative of f at z divided by n plus 1 factorial. Now, the thing to note here is this. G of a is what? Well, when you put a in here, you get 0. And f at a is the same as Pn of a. So that this is going to be equal to 0. G of b is also equal to 0 because m was defined so that it would be. If we put b in here, we get b minus a to the n plus first. We've got f of b minus this, and so that's going to be equal to 0 because that's the way m is defined. So g of b is also equal to 0. So is the derivative of g at a, because the derivative of g at a, the derivative of this is going to be 0 because we're going to get x minus a to the n plus 1. We're going to still have an x minus a here. When we evaluated a, we get 0. And the derivative of Pn is defined so that it's always equal to the derivative of f. And the derivative of g at a is 0. So is the second derivative all the way up to the nth derivative of g at a. All of these are equal to 0. Okay, so here's picture. Here's A, and here's B. And the g of A is 0, and g of B is 0. So we can find a point x1 in between A and B by the mean value theorem so that g prime at x1 is equal to 0. The function is the same on the two endpoints here, so there has to be a point in between where the derivative is 0. Now, the derivative at x1 is 0, and the derivative at A is 0. So the derivative of g at these 2 points is 0. So we can find a point x2 in between them so that the second derivative of g at x2 is equal to 0. Right? And so forth here. The second derivative of g at x2 is 0, and the second derivative of g at a is 0, so we can find the point x3 here so that the third derivative at x3 is equal to 0, assuming that n is larger than 3. Right? And we can continue doing this up through and find a point xn so that the nth derivative of g at a is 0, and at xn is 0. And now the nth derivative of g at a is 0, so we can finally find a point z between xn and a so that the n plus first derivative of g at z is equal to 0. Right? This is the mean value theorem here. Once we get the nth, then it's 0 at xn, and the nth derivative of g is 0 at a, so there's a point in between here. The n plus first derivative at z is equal to 0. But what is the n plus first derivative? It's equals to the n plus first derivative of f at x. So at z, of course, because this is at z. This is a polynomial of degree n, so its n plus first derivative is going to be equal to 0. When you differentiate a polynomial of degree n plus 1 times, you get down to 0. This is mx to the n, x minus a to the n plus 1. When we differentiate this n times, we're going to end up with m. And we're going to have the x minus a will finally disappear here, but we'll end up with n plus 1 factorial. See, when we differentiate the first time, we're going to have n plus 1 times x minus a to the n. Then we have n plus 1 times n x minus a to the next lower power, and so forth here. We'll end up with n times n plus 1 times n plus 2 all the way down to 1. So we have n times n plus 1 factorial. And this says that at this point z, m is equals to this is 0, so m is equal to the n plus first derivative at z divided by n plus 1 factorial. That's what we wanted to show. That if we just called this quantity m here, right, then it would be equal to the n plus first derivative at z over n plus 1 factorial. So that says that how bad is the approximation? It's no worse than this. F of b is approximately p n of b. The error term here is given by how big the n plus first derivative is at z, b minus a to the n plus 1. If this is small, that's going to be a small number when you raise it to the n plus 1 power over n plus 1 factorial. So that's Taylor's theorem. Okay, we want to take a look at now how well Taylor's theorem works here in terms of approximations. And for that purpose, let's start with e to the x. let's assume that x is greater than 0. And we write e to the x is equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, let's go out here to the 5th. And now the error term here says that this is going to be the n plus first derivative at some point z, which is e to the z, x to the 6th over 6 factorial. Right? So this is e to the x, where z depends on x and belongs to the interval from 0 to x. So suppose we want to approximate e to the x using this right here. And since e to the x is increasing, if, let's say, x is also less than 1, right, then this is the error term right here, or the remainder term. And e to the z, x to the 6th over 6 factorial, is going to be less than or equal to what we get if we take e at 1, x at 1 over 6 factorial. Right? So if we want to approximate e to the x for x between 0 and 1, and we go out here to the x to the 5th over 5 factorial, the error is going to be less than or equal to e over 6 factorial. Right? If we went for larger values here, right, we would end up with, for example, if x was between 1 and 2, you'd end up with e squared 2 to the 6th over 6 factorial, which is a fairly large number for x between 1 and 2. So the approximation for in the first 5 terms is not particularly good, necessarily good. For e to the x. However, this the Taylor series here does converge for all x to e to the x. Let's look at another here. Sine x. That's approximately equal to its Taylor series, but it's exactly equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Oh, let's stop there at the 8th term here, and then let's look at what do we want here. We want the value of the derivative, which is going to be sine or cosine, the 9th term here. Let's see, the function is sine x, so its 4th derivative is going to be sine x, its 8th derivative is going to be sine x, the 9th derivative is going to be cosine x. So cosine z, x to the 9 over 9 factorial. Now, z depends on x, and z, which depends on x, belongs if x is between 0 and if x is greater than or equal to 0, it belongs to 0 to x. All right. Well, if x is between 0 and 1, cosine x is less than or equal to 1. The error will be less than or equal to 1 x to the 9th over 9 factorial. Now, if x is very close to 0, then x to the 9th is going to be a very small number. Otherwise, this is less than or equal to 1 over 9 factorial, which may be an accurate enough approximation. Right? If we take x larger than 1, but let's say less than pi over 2, Then we have a sort of a dubious error term here. The cosine term here could be as large as 1, but now we've got pi over 2 to the 9th power as an upper bound over 9 factorial. Well, now, this might be a fairly large number here. In general, it will be. And so the error is not particularly good here if we look at x's between 1 and pi over 2. So for x between 0 and 1, approximating sine x this way might be a very good thing to do. For other x's, you might wish to use some sort of a different method if you're looking for a numerical value gotten by computations. Right. So Taylor's theorem and the remainder for e to the x and for sine x. We now want to look at the Taylor series for the binomial, or what's called the binomial expansion. It's the Taylor series for the function f of x equal to 1 plus x to some power. Let's say the alpha power. Right. And the reason for looking at the 1 plus x to the alpha rather than x to the alpha is that the derivative of x to the alpha doesn't necessarily exist for alpha fractional. In particular, it's not going to exist for example, if f is x to the 1/2. And so what we want is we want to look at f of x equal 1 plus x, and we'll see how this can be used to approximate various powers of a number. Right? F prime of x is going to be alpha times 1 plus x to the alpha minus 1. The second derivative is going to be alpha times alpha minus 1, 1 plus x to the alpha minus 2. Similarly here, the third derivative is alpha times alpha minus 1 times alpha minus 2, 1 plus x to the alpha minus 3. At 0, we let x equal a equal, that's to say x equals 0, we get, right here we get 1. We get alpha. We get alpha times alpha minus 1. We get alpha times alpha minus 1 times alpha minus 2 here. Huh? So for a Taylor polynomial, we're going to get p of x is equal to 1 plus alpha x plus, the next term is going to be alpha times alpha minus 1, x squared over 2 factorial, plus alpha times alpha minus 1 times alpha minus 2, x cubed over 3 factorial, plus and so forth here till we get down to alpha times alpha minus 1, alpha minus 2, up through alpha minus n minus 1, x to the n over n factorial. So that's the Taylor polynomial of degree n. I've written it down here so that it can be observed. Okay, now, if alpha is a natural number, then eventually we'll get down to 0 here, and we'll get for 1 plus x to the n, we'll get 1 plus x to the nth power. The polynomial that you get over here will be the expansion of this, which is sometimes written as the summation, n things taken k at a time, x to the k equals 0 to n, where n things taken k at a time is n factorial over k factorial times n minus k factorial. Right? That's to say, this is the binomial expansion for 1 plus x to the n, and this is exactly what you'd get here. That's to say, you're going to get 1 plus n times x plus n times n minus 1 over 2 factorial. That's going to be the second term here. N times n minus 1 times n minus 2 over 3 factorial, x cubed, and so forth here. if alpha is a natural number, then we get here is exactly the function 1 plus x to the n. For all other alpha, it turns out that this converges to 1 plus x to the alpha on the interval from -1 to 1. So that's to say if we put x in here, between -1 and 1, we're going to get convergence. Now, faster near 0. That's to say, faster when x is close to 0. That's to say, when you're looking at 1 to the alpha power. But you can go all the way down here to a small number here by letting x is close to -1. You can get as large as 2 here and compute 1 plus x to the alpha. So we can compute c to the alpha power by means of this, where c is in the interval from 0 to 2. Right? Better if c is closer to 1. So that sometimes you use a trick here, for example, to manipulate c so that it'll be closer to 1. For example, if you wanted to take, let's say, the cube root of 65, instead of using the cube root of 65, the cube root of 64 is pretty close here. You could write this as cube root of 64 times the cube root of 65 over 64, and compute the cube root of 65 over 64 using the binomial, and multiply it by 4 here. And the convergence of the binomial will be very quick in getting you the calculation for the cube root of 65 over 64. If you've got numbers which are larger than 1, if we've got some number k which is larger than 1, then 1 over k will be less than 1, and you can compute k to any power alpha using the binomial here by computing 1 over k to the alpha. So you compute 1 over k to the alpha, which will converge for the binomial, and take 1 over it. Right? Now, due to the various rates at which this converges, like I say, it converges fastest when x is near 0, or when you're trying to approximate a number, the power of a number which is close to 1. Right? You may wish to use various tricks here in order to get the convergence to occur quickly. However, this does converge to 1 plus x to the alpha on the interval -1 to 1. We're not going to prove that, but here's the binomial expansion, like so. Here's the Taylor polynomial for the binomial, and it's worth memorizing. It starts out with 1, alpha x, then alpha times alpha minus 1, x squared over 2 factorial, alpha times alpha minus 1 times alpha minus 2, the usual x cubed over 3 factorial, and so forth down the line here. Okay. But we now want to look at what I call power series, and these are things that look like they came from a Taylor series, namely something of the form summation, say, summation n equals 0 to infinity an x to the n, or summation n equals 0 to infinity an x minus a to the n power. And if this was a Taylor series, the an here would be equals to the nth derivative of f over n factorial. So for a Taylor series, an equals the nth derivative of f at a here, or at 0 over here, over n factorial. Right? This is for Taylor series. And now what we want to know is a couple of questions here. One, at which x does the power series converge? And secondly, if P of x here, if you would, P of x came from f of x, that's to say if it was the Taylor series for f of x, does P of x equal f of x at a particular x? All right? We put various x's in here, we get a series of numbers. And then the question is, does that converge? And here this will always converge when x is equal to 0. This is when we get a sum of zeros. And this one will always converge when x is equal to a. The real question is, what happens when x is different from 0 or x is different from a over here? Right? And the exact answer to this is as follows. Right? If the exact answer to this first one, at least, is as follows. If if we look at the nth root absolute an, right, and apply the root test here. Right? And if this limit, actually it's the exact root test, it's what's called the lim sup. If the limit exists, it's the same thing here. If this limit is equal to L, the root test, then P of x, right, is defined, or that's to say that you've got convergence on, it's defined on the interval from minus r to r, where r is equal to 1 over L. So that's to say, defined at minus r to r, where r is equal to 1 over the limit, actually the lim sup here, of the nth root of the an in absolute value. So to find out what the radius of convergence is here, or on what interval you've got convergence, you use the root test, right? But also, this diverges the power series does on our outside minus r to r. So anything that's outside of minus r to r, you've got divergence. Now if this limit is equal to 0, the limit of the nth root of the an absolute value is 0, then r is infinity, and this you've got convergence on minus infinity to infinity. If L is equal to 0, convergence on minus infinity to infinity. If L is equal to infinity, then you only have convergence at the single point, 0. Or if you're looking at this one here, or at the point A. Okay. Now, sometimes, in fact frequently, it's more convenient to use the ratio test when the ratio test applies. That's to say, suppose we look at summation a n x to the n, and we want to know when is it converges for which x. For which x does this converge? Well, if we looked at absolute a n plus 1, x to the n plus 1, absolute x to the n plus 1, that's the, if we fix an x, this is the n plus first term in here. Divide this by the nth term, absolute a n, absolute x to the n. We want to know, when is this limit less than 1? Right? Or is the limit less than 1? And this is the limit This is the limit as n approaches infinity, absolute an plus 1 over absolute an times x. And x is fixed here, so this can come out. Absolute x. This will be less than 1. That's when absolute x is less than 1 over the limit. Absolute an plus 1 over absolute an. So if this limit exists for the ratio test here, then you'll get convergence for all x such that absolute x is 1 over this limit. Otherwise, it's actually the ratio test that is the correct test to apply here. If this limit doesn't exist, and you'll get convergence for all x between minus r and r, where r is 1 over the lim sup of the nth root of the an. But you'll get convergence here when absolute x is less than this. So if this is 1 over k, for example, where the limit of the absolute an over an is k, and you'll get convergence there. We'll take a look at some examples. Like I say, frequently you use the ratio test here because it's simpler. But the correct test that really determines what's happening when the ratio test doesn't is the root test. We now want to take a look at some specific power series and determine the interval of convergence. Let's start with the summation 1 over n times 3 to the n, x to the n. So this is an. We want to know on what interval this converges. And here we're going to use the correct test for this. We're going to look at the nth root of 1 over n, 3 to the n. And this is equal to 1 over the nth root of n times 3. Okay? The nth root of n as n approaches infinity approaches 1. So this approaches 1/3. And so consequently, the r, the radius of convergence as it's called, is 1 over 1/3, or 3. And we've got convergence on this converges on the interval from minus 3 to 3. And it diverges outside of there. What it does at 3 and minus 3, you can't tell. It's generally not that important what it does at the end point here from our standpoint. All right, let's look at another one here. Let's look at the series for e, x to the n over n factorial. All right. And here what we're going to do is use the ratio test because it's easier. And it'll get us the same result. That's to say, when does this converge? Well, if we fix an x in here, then the n plus first term is x to the n plus 1. The absolute value is absolute x to the n plus 1 over n plus 1 factorial. This is the n plus first term for fixed x. And the nth term is going to be x, absolute x to the n. The absolute value is absolute x to the n over n factorial. And this is going to be equal to absolute x over n plus 1. And this approaches 0 no matter what x is. Since 0 is less than 1, this says we have convergence for all x. No matter what x is, this converges to some number. Now, of course, we want to know if that's equal to e to the x, and it turns out that it is. And you can see that it's equal to e to the x by analyzing the remainder from Taylor's theorem. Let's look at 1 over 1 plus x squared. Right? If we do the Taylor series on this, we'll see that we get that this is equal to sum minus 1 to the n, x to the 2n. We want to know when this converges. So here, let's take a look at the nth root of the absolute value. The absolute value is going to disregard the minus 1 to the n, and so we've got 1 is the nth root absolute an. And so, of course, this approaches 1, and so r is going to be 1 over this 1. And so we'll have convergence on the interval from minus 1 to 1. We'll look at this some more, but that's kind of interesting because here what we've got is we've got a function which is infinitely differentiable on the entire real line, and yet its power series only converges between minus 1 and 1, and diverges, for that matter, when absolute x is larger than 1. Look at one more here. Let's look at some n to the n, x to the n. Now, you might not expect very much convergence here. In fact, you don't get much convergence because what? an gets very large. If we look at the nth root of an, of absolute an, this is the nth root of n to the n, which is equal to n, and this approaches infinity. So this says that r is 1 over infinity, if you like, or it's 0. So this converges only when x is equal to 0. When x is equal to 0, of course, you get a sum of zeros. But for all other x, this diverges. Okay, so here are some power series and their resulting interval of convergence. This interval right here, since it converges for all x, is the interval from minus infinity to infinity. This one from minus 3 to 3, this one from minus 1 to 1, and this only at the point 0. All right, we now want to take a look at some operations that you can perform on power series. Right? So if we've got f of x given by summation an x to the n, and g of x given by summation bn x to the n, then we can then form, using addition here, we can form f plus g of x, and it's going to be equal to summation an plus bn x to the n. So addition here. Okay. And now, if this has a radius of convergence of r, and this one has the radius of convergence of r2, then this will converge on the minimum of those two. That's to say, between the minimum of the interval from minus the minimum of R1 and R2 to the minimum of R1 to R2. That's going to be the interval of convergence for f plus g here. All right? Similarly for f minus g. All right? Now, when we look at, so addition and multiplication here, likewise you can multiply by a constant and you'll get a constant times f. If this converges to f, then constant times it will converge to a constant times f with the same radius of convergence. For multiplication here, what we want to do is we want to look at Cn, which we would get here if we were to multiply these two together. Let's write this out. This is a0 plus a1x plus a2x squared plus a3x cubed plus and so forth here. We want to multiply this by b0 plus b1x plus b2x squared plus and so forth here, huh? Let's do the cube term. b3x cubed and so forth. Right? Now if we multiply these things out here, the constant term should be a0, b0 plus the x term is going to be a a0, b1x plus a1, b0. So this should be the x term here if we were to multiply these things out. And the x squared term here is going to be a0, beats 2 plus a1 b1 will give us x plus a2 b0. This will be the x squared term here. Right? In the x cubed term is going to be a0 b3 plus a1 b2 plus a2 b1 plus a3 b0, the x cubed. And in general here, the x to the nth term is going to look like a0 bn plus a1 bn minus 1 plus and so forth all the way down here till you get to b0 an, x to the n. And if you do this, then the radius of convergence of this resulting series, where this is C0, and this is C1, and this is C2, and this is Cn. The Cn x to the n is given by this. The resulting series will have a radius of convergence, again, equal to the minimum of the two radius of convergences for f and g. So it will converge on minus the minimum to plus the minimum. All right. So multiplication is possible here. There's a way in which you can actually do something like division, which we'll look at an example of later. Right? Two other things can be done here. Differentiation. Right? That's to say, if we've got summation an x to the n, what we'd like to do is to differentiate this and get f prime of x equals n an x to the n minus 1, the sum of these. Right? And this works. That's to say, if f is a power series, you can differentiate it term by term with the same radius of convergence. Right? Now, you can actually show that this will have the same radius of convergence as this will without too much trouble. But showing that you can differentiate it takes considerably more difficulty, and it's not really something that's generally done in calculus. You generally just take this for granted that you can differentiate. And you can also integrate or anti-differentiate. That's to say, an antiderivative for f of x with respect to x will be equal to summation an x to the n plus 1 over n plus 1 plus any constant. And this will have the same radius in both cases here. Same radius of convergence. Same radius of convergence for an antiderivative and same radius of convergence for derivative. Now this is a very useful fact. It doesn't work for just any old series. Right? In fact, Fourier series, which use trigonometric functions, do not have this property. But power series are very nice in the sense that you can differentiate term by term, and the resulting series will give you the derivative of the original function. Likewise, you can anti-differentiate term by term, and you'll get an antiderivative for the original function. We can use this fact to find out what some of the various power series are for various functions. So let's take a look at how you can get some new power series from old ones here using operations. There's one further thing that you can do here, and that's you can perform compositions, or you can make substitutions into a power series. And it's clear that if the original one converged, then the new one will converge also on the appropriate interval. So that, for example, we know that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so forth, x to the n over n factorial. Suppose we want e to the x squared. Right? Well, this converges for all x. So if we put x squared in here, it's going to converge for that too. So we're going to get 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial and so forth here plus x to the 2n over n factorial. So e to the x squared can be gotten from e to the x in this fashion like here by making a substitution, or if you like, taking the composition of e to the x here in this form with x squared. All right. Let's look at the sign of x here. This is equal to 0 plus 1x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. This is one that's worth remembering, as is e to the x plus x to the 9th over 9 factorial. So forth here. Suppose you want the sign of 2x. Well, we can get that by putting 2x in here for x. This converges for all x, so this will converge when we put 2x in here, no matter what x is. So we're going to get that this is equal to 2x minus 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial minus 2 to the 7th x to the 7th over 7 factorial plus 2 to the 9th x to the 9th over 9 factorial, and so forth here. So the sign of 2x, a substitution here. Right? Let's look at 1 over 1 minus x. Right? This is a geometric series, and it converges when, we know already, when absolute x is less than 1. The series to this is a geometric series, and it's going to look like summation x to the n. Right? Summation x to the n converges to from n equals 0 to infinity, so the first term is 1 over 1 minus the ratio is r. This is going to converge when absolute x is less than 1. All right? Well, suppose we differentiate this. This is 1 minus x to the minus 1. The derivative is going to be 1 minus x to the minus 2 times minus 1. Right? And now the theory says here that we can write this minus 1 over 1 minus x quantity squared as the differentiated power series here. That's to say the summation n x to the n minus 1. N going from 0, in which case we can start at 1 here, because when we put 0 we don't get anything. So n equals 0 to infinity. And this will have the same radius of convergence. That's to say this one converges when absolute x is less than 1, so does this one. So here's an example of differentiating this power series here. And this is the power series of this. If you compute it, you can see it. And getting this one right here. Right. We've got sine of x, cosine of x is equal to 1 plus x minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so forth. So that if we wanted to know power series for sine x plus cosine x, right, it's going to be equal to 1 plus x minus x squared over 2 factorial plus x minus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial, and so forth here. So the sum of two of them have, for the power series, this is also the Taylor series, you know, the sum of the two power series. We now want to develop a power series to approximate log of x. And unfortunately, log of x is not defined, much less differentiable, at x equals 0. So what we're going to do is we're going to look instead at the log of 1 plus x. We're near x equals 0. And we're going to actually use the properties of power series here. The derivative of this is 1 over 1 plus x. So we can write a expansion for 1 over 1 plus x, thinking of this as a geometric series. This is equal to the summation, the first term is 1, the ratio is minus x. So we have minus 1 to the n, x to the n. This is equals to 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth and so forth here. And this converges when x is in minus 1 to 1 and diverges outside of there. And it converges to this. I already know that. All right? Now, what we want to do is we want to differentiate this. So we get the log of 1 plus x is an antiderivative for this. So this is going to be x, and a differentiating we can do term by term here. Minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus x to the fifth over 5 and so forth here, plus a constant. So this is going to be the antiderivative here of 1 over 1 plus x. We want to figure out what this constant is, and for that purpose we let x equal 0. When we let x equal 0, we get 0 on this side. When we get 0 on this side, we find out that this constant is identically equal to 0. So that then this is an expansion of power series which converges on, for x, in minus 1 to 1, both of these do. And this one converges to log of 1 plus x. Now, converges faster if x is near 0. All right? Well, the conclusion here is that you can find from this you can find log of any number a if a can be written as 1 plus x in the interval from minus 1 to 1. Well, that's to say, if a is in the interval from 0 to 2. All right? For numbers larger than 2, or for numbers larger than 1 for that matter, if capital A, let's say, is larger than 1, then 1 over A, all right, is less than 1, and so you could find log of 1 over A using this expansion, and then minus the log of 1 over A is going to give you the log of A, and so you can use that fact to get the logarithm of any number A greater than 0. If A is less than 1 or less than 2, you can use this expansion. If A is larger than 1, you can get the log of 1 over A. Right? However, the thing to keep in mind here is that this expansion is quickest when x is near 0 here, and in fact it's very slow if x is close to 1. All right, we now want to take a look at a power series expansion for the tangent inverse function. Let's start out with this. 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth and so forth here, plus x to the n. This is the geometric series. So 1 over 1 plus x is equal to 1 minus x. We put a minus x in here, so we get plus x squared minus x cubed plus x to the fourth minus x to the fifth and so forth here. Let's put x squared in here for x, so we get 1 over 1 plus x squared. This is equals to 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus x to the 10th, and so forth here. Right? Now, this is the derivative of a tangent inverse function. So let's take the antiderivative of this And we should then get an expansion for the tangent inverse plus a constant perhaps. And it's going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus x to the 11th over 11 and so forth. Okay. Now this is only quick if x is near 0. The radius of convergence on this is from -1 to 1 because the original one was from -1 to 1. Well, let me mention here that this should be plus a constant, but the constant is 0 because when we take tangent inverse of 0, we get 0 on this side here, so the constant is 0. Converges quickly when x is near 0. Right? However, you can frequently trick this into giving you a result that you might want. An example historically was this. Tangent inverse of 1 is the angle of tangent is 1 is pi over 4. Right? And it turns out that this converges when you put 1 in here. That's to say 1 minus a third plus a fifth minus a seventh plus a ninth and so forth here adds up to pi over 4. However, it does so very slowly. When we get to plus a 99th here, this is an alternating series, we get to plus a 99th, we're only within 2 decimal places of pi over 4, so it's not very quick. Several methods have been used using other angles to approximate pi with the tangent inverse expansion and trick it into doing so. At any rate, this is tangent inverse of x, and this is its power series expansion, and it converges on the interval from -1 to 1. We want to find out the power series expansion for the sine inverse, and this will illustrate some of the okay, we want to look now at the function arc-sine of x and develop some Taylor series. We use the following fact. Arc-sine of x is equal to the antiderivative of 1 over square root 1 minus x squared dx. So we're going to first develop the power series for 1 over square root 1 minus x squared. And to do that, we first of all want to look at the binomial. 1 plus x to the alpha is equals to 1 plus alpha x plus alpha times alpha minus 1 over 2 factorial x squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial x cubed and so forth here. We'll just look at the first terms of this. You could, having done that, you can look at as many terms as you would need to get any accuracy you would want, perhaps for arc-sine of x. Okay, instead of x in here, we want to have minus x squared, and alpha is going to be to the minus 1/2. So let's first of all replace x with minus x. So 1 minus x to the alpha is equals to 1. Now this is minus x, so it's minus alpha x. This is minus x squared, which is the same as x squared, so we get plus alpha times alpha minus 1 over 2 factorial x squared. And we have minus alpha times alpha minus 1 times alpha minus 2 times x cubed over 3 factorial, because minus x cubed is going to give you a minus sign there. Now let's replace x with x squared in this. So we have 1 minus x squared to the alpha is equals to 1 minus alpha x squared plus alpha times alpha minus 1 over 2 factorial times x to the 4th minus alpha times alpha minus 1 times alpha minus 2 x to the 6th over 6 factorial. Right? The original thing here converges when x is between minus 1 and 1. So this is going to also, and so is this. When x is between minus 1 and 1, x squared is also between 0 and 1 in this case here. Huh? Okay. Now we want to let alpha equal minus a half. And we're going to get 1 minus x squared to the minus 1/2 is equals to 1. Now alpha is minus a half, so this is plus 1/2 x squared plus alpha is minus a half, so we're going to get 1/2 or minus 1/2. Maybe we should do this, well, let's leave this as it is, but we can maybe write this as minus a half here. Anyway, minus a half. We've got minus a half minus 1, which is minus 3/2 x to the 4th over 2 factorial. We've got minus a half times minus 3/2 times minus 5/2 x to the 6th over 6 factorial. So here now is the expansion of 1 minus x squared to the minus 1/2. That's this. And so now we want the antiderivative of that, which is going to be arc-sine of x. Right? And so an antiderivative here is going to give you x plus 1/2. Now we're going to have x cubed over 3 plus minus a half times minus 3/2 x to the 5th over 5, and this is also times 2 factorial. Minus now, minus a half times minus 3/2 times minus 5/2 x to the 7th over 7 times 6 factorial. Okay, so here's the first 4 terms, or depending on how you're counting, this is the first 7 or 8 terms of the arc-sine of x. Right? Now, we should have also included a constant of integration in here, but the constant is equal to 0 because arc-sine of 0 is 0, as is this at 0, so the constant of antidifferentiation here is 0, and so this gives you arc-sine of x. Its power series, and the power series will converge on the interval from minus 1 to 1. That's to say for x in there. Faster if x is near 0. So arc-sine of x. Okay, we now want to take a look at some possibility of dividing 2 power series by each other here. And we're just going to look at this from a formal standpoint. For one thing here, if we take, let's say 1 plus 3x and divide it into 1 plus 2x squared plus 4x cubed, for example. Right? We'd like to do this formally here, and we'd like this to be a power series for 1 plus 2x squared plus 4x cubed over 1 plus 3x. Right? Then division here by a polynomial, right, is always going to be possible if the constant coefficient here is 1. Or is non-zero. So that we can perform this division here. And if we put these now in increasing order like this, we could divide this here like so, and we would get 1. And we get 1 plus 3x. And subtracting here, we would get minus 3x. The 2x squared comes later here, huh? So we're going to get minus 3, and so we're going to get minus 3x, we're going to get minus 3x plus 9x squared, and now we've got 2x squared minus 9x squared, which is minus 7x. Oops, we should have minus 9x squared. So we have 2x squared minus a minus 9x squared, which is 11x squared. Right? And now so we're going to get 11x. Right? And you get 11x squared and plus 33x cubed. And subtracting here, 33x cubed from 4, x cubed is going to be minus 29x cubed. Right? And it's clear that we could continue doing this. And the division is going to give you a power series, and the power series will converge on a particular radius of convergence, which depends on what you're dividing into what. In fact, we could do this division here. If this went on, we could continue dividing by, for example, in this case, this monomial, but any polynomial could be divided into a power series here, providing its constant coefficient is non-zero. Right? So that we could always find, if this was 1, for example, we could always find which multiples to take to get you to the next stage in the division. Right? Now, it's also possible to divide one power series by another, and this is done by taking further and further terms along the line. Right? The question, of course, to be answered is does the resulting power series converge, and in what interval does it converge? However, let's look at the formal situation. Consider tangent of x, it's sine x over cosine x. So if we wanted a power series expansion for tangent of x, we could clearly do it by differentiating, but the derivatives of tangents get increasingly more complicated. The second and third derivatives here, because we get secant squared, and then we're going to get secants and tangents, and more complicated things here. Right? What you might like to do is the following. Take the power series for the cosine, right? Which is 1 minus x squared over 2 plus x to the 4th over 4. I'm sorry, x squared over 2 factorial, x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. Right? And let's try dividing that into the power series for the sine, which is x minus x cubed over 3 factorial. Let's change these factorials to numbers. 3 factorial is 6. Plus x to the 5th over 5 factorial, that's 120. Minus x to the 7th over 7 factorial. All right. 2 factorial is 2. 4 factorial is 4 times 6 is 24. 6 factorial is 6 times 120, or 720. And 7 factorial is going to be 7 times 720, or 5,040. All right? And so this continues. Right? But we can do this division and carry this out so far, so that, for example, if we divide this into here, 1 into x, it's going to give us x. And so we're going to get x minus x cubed over 2 plus x to the 5th over 24 minus x to the 7th over 720. Right? Subtracting here, we're going to get, what, a 6th minus a half. So a half minus a 6th is a third, so we're going to get x cubed over 3. And 120th minus a 24th. Well, this is 5 120th, so it's going to get minus 4 x to the 5th over 120, or x to the 5th over 30, yeah? Right? And I think I'll just delete this here, although we can clearly carry it through. And it's constantly what we're going to get next here is we're going to get, x cubed over 3. So we're going to get x cubed over 3. And then we're going to get minus x to the 6th, x to the 5th over 6. And I will leave off the remaining terms here, but we can clearly carry them through also. And now what have we got? We've got x to the 5th over 6, all right, plus it's minus x to the 5th over 30, which is, A sixth is 5/30ths, so we end up with 4/30ths, or 2/15ths. So our next term up here is going to be 2/15ths x to the fifth. In order to get the 2/15ths x to the fifth remainder term down here. Okay? Now these are what? The first 5 or 6 terms actually of the Taylor series for tangent of x. And if you took the 6th derivative of tangent of x or the 5th derivative of tangent of x, you'd find that you had a pretty big mess. And so that this allows you, if you know that it's going to be right, to compute the power series for the tangent function. Looking at this, let's notice something here. Notice that sine x, right, has all even coefficients. That's to say, this is x to the 0, x squared, x to the fourth, x to the sixth. And cosine x has all odd. X to the 1, 3, 5, 7, and so forth here. Well, sometimes a function f of x is said to be even if f of x is equal to f of minus x. That's to say, if it's symmetric about the origin. And all the even polynomials are symmetric about the origin. Let's say polynomials that have only powers of 2 for their exponents are all going to be symmetric about the origin. So the fact that sine x is the one sine x is the odd one here, huh? And cosine x is even. We're dividing this into the odd one over here. Well, sine x is an odd function, f of x. Sine of x is the same. I'm sorry, cosine x is an even function. Cosine of minus x is the same as cosine of x. And sine x is an odd function in the sense that f of minus x is the negative of f of x. A function that has this property is said to be odd. Right? It's symmetric about the origin. So that sine x is an odd function. It's got all odd coefficients here. Cosine x is an even function. It has all even coefficients here. The tangent of x is symmetric about the origin, so you'd expect it to be odd, and you can see that it's coming out odd here. We've got x to the 1, x cubed, x to the fifth, and so forth. All the other terms are 0. Okay, so a couple of examples of when you can, or how you can divide one series into another. Sometimes it's possible to determine the coefficients of a power series under the assumption that a solution to a particular problem is a power series. So that, for example, if we assume that tangent of x is a power series, then it's going to look something like a0 plus a1x plus h2x squared plus a3x cubed plus a4x to the fourth plus a5x to the fifth, and so forth here, huh? But now what we have is the following. And now this is analogous to the division here, but there are other situations in which you could determine the coefficients of the Taylor expansion or power series expansion of a function. What we have here is this: tangent x is equal to sine x over cosine x. So tangent x times cosine x should be equal to sine x. And now the expansion for sine x is equals to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, and so forth. The expansion for cosine x is equals to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, right, plus x to the 8 over 8 factorial. It's carried out that far, although I don't think we'll use all of that. Now, what must happen here? A0 here is the constant term in this, so that a0 times cosine x is going to give us sine x. So if we take a0 times cosine x, the constant term is going to be a0 times 1, and this is supposed to be the constant term in sine x, which is 0, so a0 is equal to 0. Let's look at the x term in cosine x. Well, it's 1, and what's it going to be? It's going to be a0 times 1. I'm sorry, it's going to be a0 times 0, the x squared term here, plus a1, the x term, times 1. Now we know a0 is 0, so that we must have that a1 is equal to 1. Right? Okay, so far we've looked at the constant term, and now the x term in sine x. Right? The x squared term in sine x is 0, and it has to be the x squared term in this product with cosine x. So we're going to get a0 times x squared over 2, plus a1 times, there's no x term here, plus a2 times x squared. h2 x squared will contribute here. a0 was 0, so h2 has to be equal to 0. The x cubed term here in the tangent x, or in sine x, is going to be 1 over 6. That's to say minus 1 over 6, minus 1 over 3 factorial. And that has to be equals to what we get when we multiply the tangent times the cosine. Right? And look at the x cubed term. Well, we're going to get a0, there's no x cubed term here, a1 times x squared over 2 factorial. So we're going to get minus a1, that's the minus sign, x squared over 2 factorial, that's over 2. We're going to get h2, there's no x term down here, a3 times 1. Okay, now we have a1 is equal to 1, so that a3 is equals to minus a sixth. This is the x squared term here. These are just the constants. So minus a1 over 2, so minus a sixth plus a half, which is equal to a third. So we get a3 is equal to 1/3. Right? So those are the first 4 terms up here, and we get tangent x is equals to, right, 1x plus a third x cubed. So the x cubed term here, we get a1 times minus 1/2, that's fine, and a3 times 1. All right, so that a3 is equals to minus a sixth plus a half is a third. Okay, so we've got the first 3 terms here. You could continue this for as much accuracy as you want, assuming that the tangent has got a Taylor series. And there are other situations where you can determine the coefficients by solving for them for the solutions to a particular problem, which gives you a function of x in terms of its power series. So I'm going to take a look at some places where power series are used. They can be used any place where you would like to have the function, but it's not easy to use the function. And one of those places is when you're looking for an integral of a particular function. Let's take a look at the integral from 0 to 1 of 1 minus cosine x over x squared. Right? We can determine that this is a bounded function on the open interval 0, 1, and that as x approaches 0, we're going to get a finite limit here. Okay? Let's, instead of integrating this, because it's well nigh impossible to get an antiderivative for it, let's replace this function with its power series. What have we got? Cosine of x is equals to its power series 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so forth here. Let's just carry it out this far. And so that 1 minus cosine x is going to be equals to 1 minus this, x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, and so forth here. Let's say minus x to the 8th over 8 factorial. Up here this would be plus x to the 8th over 8 factorial. And so 1 minus cosine x over x squared is going to be equals to 1 over 2 factorial minus x squared over 4 factorial. 4 factorial is 24 plus x to the 4th over 6 factorial, 127, 120, yeah? Okay, let's carry it this far. And now let's look at the integral from 0 to 1 of this. It should be the integral from 0 to 1 on the right-hand side here. And the terms from x to the 8th over 8 factorial on out are relatively small. If this is enough accuracy for us, we should be all set here, and so that we could get that this integral is approximately equal to 1/2 x minus 1/24 x cubed over 3 plus x to the 5th over 750 times 5, evaluated from 0 to 1, which is going to be equals to 1/2 minus a 72nd, 24 times 3, plus 1 over 750 times 5. Right, so we've got an approximate answer to the value of this integral. Let's take a look at another. This is a function that's involved with the bell curve, e to the minus x squared over 2. Suppose we want the integral, let's say, from 0 to 1 here for simplicity again, with respect to x. Well, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so forth here. Right? So e to the minus x squared over 2 is going to be equal to 1 plus, we put minus x squared over 2 in here, and we're going to get minus x squared over 2 plus, now we put minus x squared over 2 in here, and we're going to get x to the 4th plus over 2 times 2 factorial, or 4. And we're going to have, when we put minus x squared over 2 in here and x cubed, we're going to get minus here, cubing this, we're going to get x to the 6th. And, well, let's make sure we're doing this right here. This is fine. X squared over 2, this should be x to the 4th over 8 here, right? Because we just want to square the 2, so over 8. Then we got minus x to the 6th for this term. Squaring this, we're going to end up with, cubing this, we're going to end up with 2 cubed, which is 8, times 3 factorial, which is 24. Right? And for the last term here that we're going to work with here, x to the 4th, we're going to end up with x to the 8th over 4 factorial times 2 to the 8th. Right? Quite a small number. Right? And so now, the integral from 0 to 1 of this should be the integral from 0 to 1 of this. Well, what do we get here? We get x minus x cubed over 2 times 3 plus x to the 5th over 8 times 5 minus x to the 7th over 24 times 8 times 7 right? Plus x to the 8th over 4 factorial all right. 3 factorial here should be 6. Correct that. So 6 times 8 times 7. All right, 4 factorial is 24 times 2 to the 8th times, this is x to the 9th over 9. I'm going to evaluate this from 0 to 1. So what we're going to get is 1 minus a 6th plus a 40th, and so forth here. Getting these 5 terms together, and that's going to be approximately the integral from 0 to 1 under the graph of e to the minus x squared over 2. Okay, so one place where you can use these Fourier series is to evaluate, power series is to evaluate integrals. That's to say, in fact, you can use them any place where you would want to use the function, but it's not convenient to do so because the function is not easy to compute. Integration is one case like that. Okay, sometimes power series can be used for more theoretical purposes. In particular, sometimes it's easier to do certain limits with them or perform other operations. Let's suppose we want to take a look at the limit as x approaches 0 of sine x minus tangent inverse of x over x squared log of 1 plus x. Now, this is an instance where L'Hopital's rule really could be applied, but if you try and do it, you'll find that not only does it get fairly messy, but it's going to take about 6 applications of L'Hopital's rule and fill up a blackboard or a large sheet of paper. Instead of doing that, let's replace these functions here with their power series and see what happens. Sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus lower terms here, or higher terms, with higher exponents. Tangent inverse of x is equals to 1 minus x cubed over 3 really? Let's get tangent inverse of x. That's 1 over 1 plus over 1 minus x is 1 plus x squared and so forth here. Right? 1 over 1 plus x squared, we replace this with x squared, so we get 1 minus x squared plus x to the 4th and so forth. Tangent inverse of x is the antiderivative of this. So we're going to get x minus x cubed over 3 plus x to the 5th over 5 and so forth here. Minus x to the 7th over 7, so forth here. Right? Sine x minus tangent inverse of x is going to be 0, 0. Here we've got, no, I'm sorry, not 0. This is x cubed over 6 minus x cubed over 3, so this is going to be equal to a third minus a 6th. So 1/6 x cubed. 5 factorial is 120. We want sine minus the tangent, so minus a 5th. Minus a 5th is 24/120th, so this is going to be 1 over 120 minus 24 over 120, so this is going to be minus 23 over 120 x to the fifth, and lower terms. Right? Log of 1 plus x. Right? We want the expansion for this. This is equal to x minus x squared over 2 plus x cubed over 3. Right? Minus x to the fourth over 4, and so forth here. So x squared times this. X squared log of 1 plus x is going to be x cubed minus x to the fourth over 2 plus x to the fifth over 3 minus x to the sixth over 4. And now what? If we take and write our function up here, sine x minus tangent x over x squared log of 1 plus x, and we write it as the ratio of these two power series here, we're going to be able to divide x cubed out of the denominator and out of the numerator here, and so let's do that. We're going to get that this is equal to 1/6 minus 23 1/20 x squared and lower and higher terms here. In the denominator, we're going to get 1 minus x squared over 2. That's 1, I'm sorry, dividing x cubed. So it's going to be minus x over 2 plus x squared over 3 and other terms here. And now what happens here as x approaches 0, all these terms in the numerator are going to approach 0, all these in the denominator are going to approach 0, and so that we should get then that this limit as x approaches 0 of this is equal to 1/6. Right? And like I say, if you try and do this using L'Hopital's rule, it will work eventually, but it will be a very large problem because it will involve 5 or 6 applications of L'Hopital's rule with messy derivatives in each case.